In this tutorial, we're going to go over the structural geology tools in VRGS. I'm going to start with a blank project, File, New, and we'll give this a name. So I'm going to call this Structural. That generates the blank project for us. We'll then take a look at some data. We're going to import this data set. It's an OBJ file. When you have an OBJ file, you will usually find that alongside it there is a material file and the textures. These all need to be in the same folder, but you only need to drag and drop the OBJ file into VRGS to import it. And if I look in my messages panel down here, it tells me that it's importing the OBJ file. You can also import directly into the mesh group using a right click on the triangular meshes group and then go to import and from file. Now, when it first brings the data in, it will do some extra processing on it. So it's still reading the individual sections of the mesh for the textures. It's doing some optimization on the mesh now, and in any moment now we should be finished. This pre-processing is only done when you first import the data. You don't have to run through this every time you open the project. So there the mesh is written to projects, written to the project file. If I look at the mesh in the data tab, it has a little status box next to the mesh. If it's this color, it means the project needs saving, or the mesh has changed and needs saving. If it's green, it's already saved. So if I click save now, it will write that project to disk and write the mesh to a disk, and green and ready to go. So let's just go over the different panels and menus that we have that we'll be using throughout this tutorial. We've got the ribbon bar across the top of the screen, or the ribbon menu. We'll be working mostly in interpretations and a little bit in the home ribbon menu. On the left hand side of the screen we have the data tab, where we have things like our point clouds, our meshes and our satellite images. And there is also the interpretations tab, where our polylines and orientations will go. Then there's another tab called collections. These are things that can't be visualized directly. So they are descriptions that are attached to other objects. The interpretations and data tabs have things that can be visualized in the 3D view. At the bottom of the screen we have the messages panel, which gives you status updates of what VRGS is doing. And then on the right hand side we have our properties. Any of the objects in the data interpretations and collections tree, if you click on them, you get the properties that you can change. And sometimes it just gives you information on the object that you're selected. So you have group properties. These are display options and settings that apply to the whole group, and then select the individual items, objects, and you get the properties for the individual object that you're looking at. As well as the properties panel, we have charts, where we look at histograms and stereonets, and we can switch between the two views using this menu buttons across the top here. And those are the main panels that we're going to be using. So let's visualize our data. So just select the checkbox. It's now bringing that data, transferring it to the graphics card. So it might take a moment or two. And there we go. Again, on the first visualization, it has to do a little bit of processing, and you can see in the messages panel that it's built some textures. So it does some compression on the textures to make loading them quicker. Again, that's a one pass. It won't need to do that again. And here is our digital outcrop model. First thing that we want to do with an outcrop model like this is put a scale bar on it so we know the size of the thing we're dealing with. So there's our 5-meter scale bar. I can select the scale bar in the 3D view by clicking on it and go to the properties, and I can change the properties of the scale bar here if I need to. So we could make it 10 meters high. We could have 10 segments on it, so 10 1-meter segments, and change the color and so on, however we see fit. We can also change it to be a horizontal bar or a triaxial bar, and we can change the orientation of the bar if we need to. The first structural geology tool that we are going to look at is the dip azimuth tool. The dip azimuth tool has several different modes to it. The way VRGS works is when we have a split button like this, you can see the button has two components to it. The top half of the button is the most commonly used method, and then extended methods are in the drop down part of the menu. So typically we would create a dip and dip direction with 3 points. So 3 points form a triangle, and if you have a triangle, it defines you can use that to define a plane and calculate the orientation from it. The default method, 3 points. So let's find a bed. We're going to select this bed here and go 1, 2, 3, and I'm selecting the points as close to the bedding plane, exposed bedding plane, as I can, and going round a corner. So if those 3 points are in a perfect straight line, you can't calculate an orientation. It has to have some 3D shape to it. And there's our structural measurement, first structural measurement, and we're dipping at 4 degrees towards 194. If I then select the charts panel here and switch on the stereonet, we get a display of the orientations shown. Now this stereonet is tied directly to whatever is displayed in the 3D view. And what that means is if I then go on and make another measurement here, so let's put another measurement around one of these other beds. So dip azimuth, 1, 2, 3. It automatically appears on the stereonet. At this point, I'll just clarify that VRGS always gives you dip and dip direction or dip and azimuth. It's not strike and dip. The azimuth, it will be 90 degrees from the strike. And that's a common question that I get, is why is VRGS's directions appear to be 90 degrees out from the strike? It's because it always gives azimuth. So they are correct. The next thing we'll look at is a slightly different mode for the orientations. So dip azimuth, we can do dip azimuth by endpoints. And for this, instead of just selecting 3 points, I can add in multiple measurements. Double click to finish. We get a slightly different but fairly similar value. You might expect variability as you go up and down the section. But here we're calculating this orientation from several points or multiple points, more than just the 3 that we used up here. This is quite a useful mode if you're trying to get the geometry of something where you've got a lot of complicated shape on the outcrop, or if you want to delimit the shape of a fracture, the exposed area of a fracture using the structural mapping tools. And again, on our charts panel, we see how bedding measurement is displayed. Right, so we've done some structural measurements. Let's look at mapping a fault. We're going to do all our mapping here using the polyline. There is a fault mapping tool, but in the next update to VRGS, digitized fault and digitized polyline will be merged into one option, and it will all become digitized polyline because they basically do the same thing. And you'll be able to define whether you're digitizing beds, faults, or whatever by giving it a name and putting it into separate groups within the interpretations tree. So we'll just stick with using the polyline. Right, digitized polyline. Again, there's a few different modes here. First mode, individual points. We select our points. If I hold down the Shift key, I can move the model around without coming out of the digitize mode. It just pauses digitize while I move, so this is useful when you want to go around a corner. Carry on clicking points, double click to finish, and there's our polyline. Now the polyline also has an orientation attached to it. It uses the same approach for the endpoints dip azimuth. If we look at the properties, there will also be a dip and dip direction associated with it. Now, the reason why we have the structural measurements and the polylines separately is that when you're digitizing a polyline, you're more interested in delimiting the shape of a feature. You're not necessarily worried about getting the orientation of it. If you're using the dip azimuth tool, your focus is getting a good structural orientation. This does mean that sometimes when you draw the polylines, the polyline that you end up with is not necessarily good enough to get an orientation from. You can then add a structural measurement that you've taken specifically, or one that you've collected from the field, and update the value of the polyline that you've just drawn. So we can probably demonstrate that in a moment. I'm going to switch to back to drawing polyline. This time I'm going to use the draw mode. So the draw mode here allows you to drag, and it will put in lots of vertices, or I can just do single points like we did before. Can drag down there, double click to finish. And here's an example where it's probably not giving us a particularly good representation of the true strike or the true orientation of the fault, because it's being dominated by the shape of the outcrop itself. We might decide that we want to assign this the same orientation as this fault here. So if I go back to this polyline, and in its properties, I'm going to just switch on extrude along strike, because that tends to look a little bit better when you're working with steeply dipping polylines. And our orientation is 43.4 towards 282. And you can just update that in your properties there. And of course we could have done that by making a measurement using one of making a dip azimuth measurement and attaching the orientation from that to this polyline. when we're dealing with faults, we quite often find that the fault is not a single plane. It is actually a set of strands or set of segments that are joined together. We can map those in VRGS and maintain the connections by using the snap vertices tool or approach here. To do this, in polylines, let's switch on polyline group. We can switch on show node. So that will make sure that all the vertices are shown all the time. I will change the size of the vertices on this to make them a little bit smaller. And maybe we want to add in that there is a strand of this fault that goes along here. I'll go to my digitize polyline tool, and we've got the snap vertices mode switched on. And here now we can see that when I select these polylines, that this vertex, and there's a vertex here as well, that is shown in a different color. That means that that vertex is shared between these two objects. So even though we've got two polylines, in this case, there is only one vertex here and it's shared between the two polylines. That means that connection is stored internally in VRGS. Again, let's look at, we were 43282. Let's just use the same orientation here because that polyline doesn't have enough 3D shape to pull out an orientation. So you had 43 and 282. And we want to do our extrude along strike, and there is our fault segment added in, or the strand. We can edit our vertices now, or at any point. So here's move vertices. This mode allows us to move a vertex. The vertex is always attached to the outcrop. It sticks to the outcrop model. So wherever I move it, stays on the surface of the model. There is another mode, which is this 3D translate mode, where I select a vertex. There we go. Oh, there we are. Sometimes you get this where the widget that we're going to use to move the vertices can appear a bit too small. Hold down the control key and use the mouse wheel, and it changes the size of the widget that we're going to use to move this in 3D. So if I select one of these planes, I can then move this vertex around in 3D. So it's control and mouse wheel will change the size. And then just select either the planes or the axes to move it around in 3D. You can, of course, go back to the move vertices mode, and it will snap it back to the outcrop. So we've started to build up our interpretation of the fault. Let's look at measuring some displacement on it. Well, what we can do here is we need to find out what is similar, what are the same beds over here as over here. And for this one, it's quite easy. We can look at the beds here. These are locally known as the stripe beds. And if we go over here, you can pick up the same beds higher up on the cliff face. There's a lot of dirt being washed down from here, so they're not as well exposed. But once we've seen that, this mudstone interval here with this line of concretions coming through the center of it is the same as this mudstone here. Let's interpret our bed on there. So digitize polyline, top of this thick bed at the just below the stripe beds. Shift key, and I can move till we get to the fault. Double click to finish the line. Across the fault. Stripe beds are there, stripe beds are there. This thick bed is this thick bed here. Digitize another polyline. Double click to finish. Again, jump. Double click to finish. And final one down here. And there we go. So we've got a set of polylines in there. We need to organize these in our interpretations. We can do that very easily if I select an object in the 3D view and then click on the interpretations panel to give it focus. You'll find that the thing that you've selected in the 3D view is highlighted. So if I then do the same for this one, it's polyline 0. So we know that polyline 0, we can do it by switching them on and off. And polyline 2, you can also right click on one of these and do a go to, and it will take you to that particular object in the 3D view. So these are our faults. I'm going to group those, and I can change this to faults. Then these, we can do a group, call this beds. I can add some descriptions to them by using this tool up here. At the moment, there's no horizon names. We can add some in. I'm just going to add a couple and use the default values. So let's call this surface pick one. And we do that by going to the properties and changing the stratigraphy to pick one. And there we go. If I want to then interpret another horizon, I could change that in here, or select the active horizon in here. For example, I'll go to pick 2 and make that active. Digitize polyline along here. Double click, and it automatically will be assigned whatever is in the active horizon here. And if I go to click on it in the interpretations tree and look in the properties, it's been assigned pick 2. If you want to change the naming convention, select the group and you can modify the default name here. So at the moment it's called polyline. We could change it to be bedding, And also we can add some variables. And if you look on the VRGeoscience documentation site, you can find the list of variables there. But here we'll add the current date and time to the measurement as we make it into the name. Name counter, we can reset that to 0 and it will start counting from 0 again. Let's do another polyline just to show that. Digitize polyline. Double click to finish. And there it's changed the name. It's gone to the default bedding, reset to 0 and put the date in. If we want to put these together, all together in the same folder to an existing folder, I can select them and just drag them in. And of course, we might want to put these into separate folders as they are separate beds. So that's dealing with polylines, making structural measurements, and being able to organize your data in the interpretations tree. The next step is to use some attributes. I'll start to generate an attribute set. Go to your mesh, right click, attributes, tensor analysis. And after a moment, we'll get the tensor analysis dialog box. The tensor analysis, there's a couple of approaches that it uses. There is one approach we can use, which is a radial basis function. What it does, it will go through each vertex in the mesh and find all the other vertices that lie within this distance of the vertex that we're looking at. So all the vertices that lie within a sphere of that radius. I'm going to edit that and use 0.1. The estimate that the tensor analysis dialog box gives you here is generally pretty good. It can do that on meshes because it uses the edge lengths as the triangles to make the estimate of what the sphere should be. Can't do that on point clouds because there aren't any triangle edges unless you create a mesh from them. But a good rule of thumb is if you know what the average data spacing is between your points on the outcrop, your vertices on the outcrop, then use twice that. And that's a good starting point. What you can then do is once the tensor analysis is run, you can look at your number of observations attributes. And if you've got a lot of zeros and ones, then you might want to make your sphere radius bigger because you need at least 4 points for the in that sphere for the tensor analysis to work effectively. The other approach is to use k nearest neighbours. So rather than using a sphere radius, it finds the nearest 5 neighbours and use that. But we're going to go for the sphere-based approach. So I'll do a check all. Leave the octree settings as they are, generally around 7, 8, 9 are good values. And we'll let the tensor analysis run. The model will disappear while the tensor analysis is running. That's because it's processing the data, so VRGS doesn't want you making changes or edits to that data while it is actually processing. Now, why do we use tensor analysis? Well, the RGB data, or the model that we look at typically, which is the photorealistic RGB red, green, blue view, is very good. It looks like what we expect to see when we're in the field. But there's a lot more information in the outcrop model which can be derived from the geometry of the surface itself. So how rough the surface is, what the angles are, how does the curvature of the surface change. And the tensor analysis allows us to generate a set of attributes that mean we can visualize those changes and use them to assist with our interpretations. This will take a moment or two to run, so I shall pause this for a moment and come back when it's completed. Our tensor analysis has nearly finished processing. It's taken a few minutes for this to run, and we're dealing with a model here of around 3.5 million vertices. Obviously, bigger models will take longer to run. Sometimes on really big models, this can be an overnight process, but it's a one-off. Once you've generated the attributes, they'll be saved and you won't need to do it again. On the data tree now, we have our object, our mesh with all of the attributes associated with it. These are the ones that we've just generated. So we'll have dip, which is the dip of the surface, a dip of the outcrop. So it's not the dip of the beds or the fractures unless it's an exposed fracture plane or bedding plane. It's the dip of the surface. Then we have the azimuth, which again, the same thing. This is the azimuth of the outcrop surface. If I go to the charts panel and now switch to histogram to look at the histograms for the attributes, we have our azimuth, our dip, and coplanarity. So coplanarity is a useful one because that tells us how flat the surface is. Our azimuth attribute is shown as a histogram. Typically, we would want to see this as a rows diagram, and we can do that by going via the Collections tab and creating a new color map or importing a color map. So I'm going to do that. So I can import a color map. A useful website to know about is this one, colorcet.com. Has a whole load of perceptually uniform color maps. So it means that these color maps are designed not to introduce bias into the way data is displayed. We're going to use one of the cyclic color maps from this website. So you can download these color maps from here. I'm going to bring in the CSV file, bring in a cyclic color map, and we need to find it in our collections panel here. So we've got color maps. Go to the properties, and you can see the colors there for each individual level has a separate color. It's got a name at the bottom there, and we switch on continuous and cyclical. I'll go back to the properties of the attribute, the azimuth attribute, and change the color map from the default to that cyclical color map that we've just brought in. And you see the color and the display changes straight away. But if I now go to charts and look at my color map there, it's represented as a radial or cyclical color map. Gives us a more of a rows diagram kind of view, which is more appropriate for this kind of data. If I look at dip, for example, and look closely at our outcrop model, you see in the histogram we have a spike and low dip, so that's going to represent these dark colors, the exposed beds on the foreshore here. And looking closely, the dip attribute is starting to pull out. We can see the stripe beds in here and pick out the bases and the tops of some of these beds. Coplanarity is a particularly useful attribute for us. We have to edit this column, this attribute. You tend to get a lot of very high coplanar values. So we need to sort of stretch this histogram. We do that by, on the charts panel, when the histogram is displayed, there's a red line and a yellow line. These are your filters, and either one, you can click on it when you see the cursor change to the double arrow, and then we can drag that filter and you see the color in the 3D view change to match the range in the histogram now. And I'm going to drop my filter down to about somewhere around 4.5. Values of over 4 for coplanarity tend to be quite flat, and that is then a good way that you can use to sort of identify things that you think might be exposed bedding planes and fracture planes. For example, here there's a couple of sort of distinct orientations that are being picked up, and we can see certain planes and orientations repeating over and over again. We could go through and use the 3-point approach for any of these like we did before. So I could go to dip azimuth and say 1, 2, 3 to get a measurement. And again, that will appear on our stereonet. But we already have, through the tensor analysis, the dip and dip direction of the surface as part of the attribute. There is a tool in here called dip azimuth from attributes, where I can just click one point and it will pull out an orientation from the surface attribute. Now we've done 2 on the same fracture plane here. They come out slightly different. We've used different approaches. You need to check your data and make sure that you've clicked appropriate points to do your 3 points, or you've clicked an appropriate point to get your 1 point from. But you will get variability. I can use attribute again, select one there. Now it's not particularly efficient having to keep going back and reselecting the attributes option. We can switch on. So I've just switched off the snap vertices. We don't need that at the moment. Switch on sticky interpretation. This locks the mode, the interpretation mode, so it doesn't keep resetting back to the default move mode when you've finished interpreting an object. So if I now go to attributes, I can select that, and let's put one in here. Of course, you would spend a lot more time doing this if you were doing this for real. So let's say that there's one there, there's one there. Can go and pick out along here, and as I'm selecting these points, it's pulling out the orientations from the attributes and plotting it on the stereonet view directly. So it allows you to see what's happening with your structural data in real time as you're interpreting it. Again, you would spend a lot more time making sure you were doing good interpretations than I'm doing here. I'm just doing this very quickly for the sake of demonstration. But you can see how that can build up very quickly. While we're looking at this particular stereonet, I will introduce the other stereonet view, where we can go to the home ribbon bar and select Windows stereonet window. And I can drag that tab to give us a side-by-side. And we can obviously move this and zoom in and out again with the mouse wheel like you can on this one. Now, immediately you'll see these are different, that this has the structural measurements on it, this one doesn't. The tab, the stereonet tab, is tied to the 3D view. The stereonet window is independent of the 3D view. So if I'm on, give the 3D window focus, you see these are all now selected. If I give the stereonet window focus, they're all unchecked. And I can just switch on a subset of these in the stereonet window. So that's the key difference between the stereonet window and the tab. Tab's tied to the 3D view, the stereonet window isn't, and the stereonet window has a bit more flexibility in what you can do with the data. So let's talk about that. If I switch on all of my interpretations that we've got so far, I can switch on contours, I can have a solid fill, I can change in the stereonet window, so click the window tab, and in here we can update things like the color table that we're using. So I could switch to plasma instead. I can switch off the planes and just see the poles. I'm going to switch off the contours, and we can do, for example, use the selection tool. So I'm going to use elliptical selection and select those. If I now give the interpretations tab focus, what I've selected in the stereonet is now selected and highlighted in the objects in the interpretations tree. So I could then go to group those, and then that could become our bedding group. And we can go on and do a similar thing if we want to with our orientation measurements. So I could go to my ellipse here, select those, select them individually, do a group, and have those as a separate group, which we can then also go back to our structural window here, and we can switch them on and off. There they are. Similar orientations. You can have as many groups and subgroups as you want within the interpretation tree. Next thing to look at is the ortho panels. The ortho panels are a way of viewing your data with the structure and the, well, not the structure removed, but with the perspective removed and projected along a particular orientation. To do that, we're going to go to, let's switch off all of our current interpretations. We'll go back to our data panel. I'm going to switch off my coplanarity attribute, and I will put into here a structural measurement from 3 points. So I want a good structural measurement from around here. Still in sticky mode, let's switch that off. You can always go back to the move mode, standard mode, by clicking this button up here. This cancels any interpretation modes that are active. And now we have a structural measurement that's giving us the strike and the dip or the fault at this position. The ortho panel tool is in the interpretations ribbon. Again, it's a split button. we have extended modes where we can do ortho panels by 2 and 3 points. In this case, I'm going to just use the default mode, which creates the ortho panel based on a structural measurement. So I'm going to click the structural measurement here, and the ortho panel will be generated looking down dip by default. If I double click on the ortho panel, we get the handles appear. That means it's active. Using the middle button, so I'm holding down the mouse wheel for this, and you can move the panel around. If you use the mouse wheel, it moves the panel forwards and backwards along the projection direction. Now we don't want, in this case, to have a dip view. We want to have a panel where we're projecting the data along the fault strike. So the ortho panel would give us an effective dip section through the fault. I go to the panel properties, and I'm going to change it from being a dip panel and switch on strike panel. So that changes the orientation. So now you can see it's moving around here. Move it out. I need to change the width. I'm going to make it 60, and I'm going to make the height 30. That gives us a much bigger ortho panel. We can leave the grid switched on if we want. The grid that it's displaying here, the size of the grid is defined in the attributes of the mesh. So down here you can see we've got grids, a grid interval of X and Y. So actually I'm going to switch off my grid. If I want to do that, I can switch off the bounding boxes. And then we can move the ortho panel around, and it now updates without the bounding boxes. Also note that the scale bar gets projected onto the ortho panel as well, so that's good if you want to incorporate a scale. As I move further away, you see that the projection, you start to lose parts of the projection. That's because the projection only will work for a certain distance. So if you go too far away, it no longer projects. That gives you a bit more flexibility. You can change that by modifying the near clip and far clip planes. Just going to put that up to 80, and it should project everything again. And this, the near clip and far clip planes, they're sort of a dimensionless parameter. It's to do with the way that the graphics are projected in 3D and the transform that's defined for that. So you can, it's a bit of trial and error to get the values right on that, but it's not too difficult. Just update them and change the values. The default's usually pretty good. The other thing that we might want to do here is change the resolution on the ortho panel. So I can change the pixel size to 0.2, give us a bit more detail. And now we have a nice image of the fault looking directly along the strike direction. So the panel is itself is oriented along the dip direction of the fault, and it has all of the perspective of the 3D view removed. I can export my ortho panel through going to export here. I'm going to give it a name. I'm just going to call it test.bmp. And there we go. There's test.bmp bitmap file. There. Now it's coming upside down and back to front. That's because an ortho panel is a three-dimensional projection. when it's generated, it doesn't really have any concept of what's up and down. It can be in any orientation to give you maximum flexibility in defining your ortho panels. We can fix that simply using the edit mode in your favorite editor and just flip it into the correct orientation and then crop it as you see fit. So there's our orthographic projection. And of course, the orthographic projection is rendered from the 3D model itself. So whatever we have displayed on the 3D model, so if I switch to coplanarity and then update my ortho panel, it will show the coplanarity attribute or the collinearity attribute here. So that we need to collinearity, we need to go to charts. This will always need some updating. It's not always the most useful attribute to look at. I can then on here go to transforms and clamp to filter. That removes those high values permanently. And then I can bring these down even further. So again, is pulling out some information. So then we'll go back to look at dip and dip direction. Update the ortho panel, and there's it updated, and of course you can export that with those attributes displayed. Sometimes you might want to do a false color version of your data, of your model. We'll do a false color representation based on dip direction or azimuth, and the coplanarity. If you want to do this kind of false color, we need to actually do a clamp on the data like we just did with collinearity. So I'm going to do the same thing on coplanarity. So I'll do clamp to the filter. So it clamps these high values down to whatever the filter is, effectively giving us a contrast stretch on the attribute. Then I can go to the mesh object, go into properties, and in here I can change what we're using as the RGB channel. So I'm going to use red for dip, green I will use azimuth. When you're updating the properties like this, as you update each property, it quite often has to regenerate the mesh, which can slow things down. If you find that's a problem, you can switch this option off here, this button off here, which is the auto update. Then I can just change this to azimuth, and I don't have to wait till go to change this to coplanarity. Then I will have to force an update with this button, or switch auto updating back on. And it's just rebuilding the mesh now with the new attribute. And I have to, in the properties here, switch off the texture map so we can see the RGB colored vertices using our false color image, combining the coplanarity, the dip, and the dip direction. So that can help us with our interpretation as well. While we're looking at ortho panels, we'll switch our texture back on. I'm going to get rid of this ortho panel, and we're going to use the ortho panel approach to do a template match across a fault to make sure that our correlation is correct. So quite often when you've got a fault, it can be sometimes difficult to work out what the displacement is and to match things across either side of the fault. If you look at the quick tips on YouTube, you'll find an example of this, but we'll just generate a quick one here to demonstrate the principle. I'm going to use interpretations author panel by 3 points, and I'll use 1, 2, 3. Double click to activate the author panel. Mouse wheel to move it in and out. I'm not going to change the size of it, but I will increase the resolution. And I will. So as I move the ortho panel, it automatically updates the projection. I can switch off auto update in its properties, and now that's fixed. It doesn't change the projection. It's the fixed image. I'm going to quickly change it to a strike panel. And if I move it there, we can easily see that, of course, it comes from that position, but it's easy to see how the beds match up. I can now move this across to the other side of the model. So remember, mouse wheel moves it along the projection direction. Middle mouse button holding down the mouse wheel moves it around. You can also use your left and right mouse buttons held down together. But it's best to use the middle mouse button if you can. And then we can see how this matches up with this side of the outcrop. And there will be a little bit of variation in the thickness, but there are stripe beds matching up here. This bed matches the one that comes over here. Then you have this sort of area in the middle of the muds that has some little concretions in it, is picking up in there. And then there's our lower bed as well. So that allows you to pull out a panel from one side of a fault, move it across to another, and check that your correlation is correct and that you've got your fault displacement correct. Final thing to look at is using cross sections. I'm going to add my cross section in from here. I'm just going to do 1, 2, 3 points or 4 points, double click to finish. It automatically puts the cross section in empty. Now you probably have a decent cross section already drawn. You can put this in different orientations, but a case that I was asked about the other day, it was that somebody wanted to bring in an image of some seismic data and stretch it to match the fault. Now, I don't really have any seismic data that matches this. It's completely the wrong scale. But we're going to pull in a small piece of seismic and look at how you can manipulate the cross-section to fit the data together. In my interpretations panel here, I right-click on section and go import bitmap or import image. And let's bring in, for the want of a better, well, actually, let's bring in from, I'll find a bit of seismic to bring into this. There we go. There's a little bit of seismic data. Again, I have to stress that this is, this is not scaled correctly or anything, not really related to this outcrop at all. We're demonstrating a principle of how you can edit and move the cross section around and scale it to something more appropriate for what you're working with. Just demonstrate how the tools work. Again, we use this 3D translate, and when I select this tool, you should see on the cross section some handles appear. So we have a sphere in the middle. If I select that, again, remember I can use the control key to change the size of the widget, and this allows us to move the whole panel around in 3D. If I select the top handle, that just allows me to move the section up and down and change its scale. If I select any of the handles on the bottom, these are the original points that we put in, and we can move these around and change the shape, the map view of the cross section. If, as I'm moving this around, you can see that the position of the inflection point in the cross section moves as I'm moving the inflection point on the section vertices. Sometimes we don't want that to happen. Say if we'd got a section which was imported that had a series of different panels which weren't necessarily at the same scale, we would then go to our section properties and switch off this option here called Auto Update UV. And now if I move that around, go back to moving this around, it doesn't move that inflection point in the image, even though it's moving it on the panel itself, on the geometry of the panel. So you see now the scale of the different segments of the panel are changing as we're moving the vertex around. So that gives you quite a lot of flexibility in being able to define your cross section and change the way in which the image is displayed on it. And of course, you can go on to this cross section and also digitize and put points in. Now that's coming completely vertical because obviously this polyline, this line is completely straight, so VRGS can't calculate an orientation for it because it's straight, so it will just put it in as vertical. So I can now update the orientation of this polyline, set it to 0. And of course you have to remember we're interpreting on a bitmap, we're not interpreting on seismic data itself, it's not a seismic interpretation program, it's just drawing a polyline on the surface. But I think you can see how flexible that can be. And of course you can use this approach to have a section that comes out of the outcrop and extend your interpretations away from the outcrop. You can do that similarly with the ortho panels. So if I go back to my original ortho panel that we did here, let's switch off this cross section. Double click on that, move it back into the correct place. We have our polyline auto interpretations here from the faults that we've already done. Yep, there they are. You can see them displayed on the ortho panel. Just there. But we can also use the ortho panel to extend our interpretation if we want to. So I'll go back to interpretations and deactivate the ortho panel, digitize the polyline, and we can just put in, trace along the same position if we want to. There it is. Let's switch off that ortho panel. Say this polyline, if we remember our dip 43282, This will give us a vertical because it's mapping the shape of the orientation of the ortho panel, not of the outcrop. So 43,282, 43,282. We're going to do extrude along strike. Then I'm going to select the two segments and modeling tab, build surface. We have a new mesh has appeared in the triangular meshes, and there it's created a surface. That gives us a fairly basic representation of what this fault might look like if we're projecting out into 3D. Of course, it's an interpretation. You might want to take into account what's happening down here, that it's fairly clear that this fault isn't coming out directly like this, it's actually coming out this way, so we would have taken that into account when we did our ortho panel. So we could have done it by switching off auto update, and then we can move our ortho panel around. We can say, well, okay, I think my fault is actually coming out to around there. Digitize my polyline in around there. Could have brought it out there as well if I wanted. And then used a similar approach to changing the orientation, selecting the polylines and building it out into 3D. Okay, that's an overview of some of the tools for structural geology and interpreting faults and beds and fractures. You can find more tutorials on YouTube. Make sure you follow us on social media, follow us on LinkedIn, and keep an eye out on Eventbrite for future workshops. Thank you very much.